It's Professor Adam. Let's talk about orbital hybridization. We've already learnt about electron domains in a previous video, but to recap, if we take carbon dioxide, there are two areas of high electron density where the carbon-oxygen bonds are formed. These can also be called electron domains. One way to visualize or approximate the formation of these domains is through orbital mixing. The carbon atom combines two of its orbitals, the s and p orbital, to create a new sp orbital. This process is called hybridization, and the sp orbital is referred to as a hybridized orbital as we have mixed the two orbitals. The two electron domains give rise to sp hybridized molecular orbitals. For now, the number of electron domains can be counted and used to approximate how many orbitals will be hybridized by the central atom to satisfy the number of bonds. Usually, the orbitals s, p, and d are involved in hybridization. For a typical energy level, there is one s orbital, 3 p orbitals, and 5 d orbitals. For the previous carbon dioxide model with two electron domains, two orbitals are needed, the 2s and the 2p. When we have an sp hybridized orbital, the geometry is linear with a 180-degree bond angle between electron domains. When we mix 1s and 2p orbitals, we end up with an sp2 hybridized molecular orbital. 3 orbitals hybridized means 3 electron domains, likely resulting in 3 bonds, such as in trifluoroborane BF3. sp2 hybridized molecules will have a trigonal planar geometry with an angle of 120 degrees between electron domains so that the fluorine atoms can be as far apart as possible. When we get to 4 electron domains, there are 4 orbitals that will be hybridized, 1s and 3p orbitals, to give an sp3 hybridized carbon atom. To understand this geometry, 3 dimensions are needed. Bond angles between the carbon-hydrogen bonds are 109.5 degrees in this methane molecule. Methane is an example of a molecule with tetrahedral geometry. Atoms with 5 electron domains are sp3d hybridized and adopt a trigonal bipyramidal geometry with bond angles of 120 and 90 degrees between the electron domains in order to reduce repulsion. Atoms with 6 electron domains are sp3d2 hybridized as we mix 1s, 3p, and 2d orbitals. They adopt an octahedral geometry because if the points were connected, they would form an 8-sided shape. The bond angles in an octahedral complex are all 90 degrees. These electron domain geometries and hybridizations apply equally well for molecules with lone pairs. We can simply count the number of domains, either of bonds or lone pairs, and then use this to determine the domain geometries. Molecular geometries, though, can differ from their electron domain geometries, as we will see next. Ammonia has 3 bond pairs and 1 lone pair, giving it 4 electron domains with the sp3 hybridization on the central nitrogen. This gives it a tetrahedral electron domain geometry similar to methane, but its molecular geometry is different, and we assign it the trigonal pyramidal geometry. Water also has 4 electron domains, 2 bonding and 2 lone pairs, meaning that the central oxygen is sp3 hybridized. The repulsion of the lone pairs causes the water molecule to adopt the bent geometry. This means that it will have the usual sp3 hybridized tetrahedral electron domain geometry, but will have a bent molecular geometry. It is important to understand why carbon dioxide and water have different geometries. For more on this, please refer to the VSEPR videos linked in the description below. It must be remembered, though, that orbital hybridization is an oversimplification and it cannot be explained from first principles. For example, it is impossible to tell the degree of orbital mixing in the water molecule. Orbital mixing and hybridization does have some use in helping to visualize bonding, however. But a better model is VSEPR, and only molecular orbital theory can provide a full picture. Let's check comprehension.